Hi everyone, what we're ready to embark upon now is a walk through the development of integral calculus and the problem from which it came, the problem of finding area under a curve. And we're going to take a very historical viewpoint of this so you hopefully get a good understanding of where all this came from. At this point you have studied antidifferentiation, which you will remember is the problem of finding the equation of an original function from that of its derivative. What we turn to now is the problem of finding the area of a region in the Cartesian plane. And it doesn't seem like the two would be very related to each other, but you're going to see by the time we're done that it very much is. So let's take us back a ways to about 4th, 5th century BC. And the problem that I guess you could say sort of started it all, the idea of just finding area of a circle. Now back around 4th, 5th century BC, they didn't know what pi was. Pi had not yet been quote-unquote discovered. So if we're trying to find area of a circle, pretend you don't know pi r squared is going to give you the area that you want. So if you didn't know about pi, how would you find the area of a circle? Well, mathematicians back then did know how to find area of polygons. So one thought was, well, let's inscribe a triangle inside that circle, and we know how to get area of a triangle. But as you can see, that area of the triangle would very much be an underestimation for the area of the circle. Instead of inscribing the triangle inside the circle, well, what if we circumscribed the triangle around the circle? That then is going to give us an overestimation as to the area of a circle, because obviously the area of the triangle is going to be much larger in this case than the area of the circle. So maybe you think, okay, well maybe take the average of the two, and maybe somewhere in the middle would be something somewhat like the area of a circle. Might be a good guess. So what mathematicians started playing with was, well, what if we started using different types of polygons? Polygons with an increasingly number of sides to them. So what if instead of using a triangle, we were to use a square inside of the circle? Well, that's still going to be an underestimation, but maybe not as much of one as we got with the area of a triangle. Or maybe we could circumscribe the square about the circle. Again, it's an overestimation, but maybe in averaging the two areas together of the square inscribed and circumscribed, maybe we'd get something a little bit closer to the true area of the circle than what we got with using a triangle. Well, let's increase the number of sides even more. What if we considered a hexagon with 6 sides? Still an underestimation, but definitely closer to the area of a circle. You can see you only have, this empty space here. Or maybe we could circumscribe that hexagon about the circle. And again, maybe using this averaging idea, between the area of the hexagon either inscribed inside the circle or circumscribed about the circle, maybe again somewhere in the middle, would be a good estimate for what the area of the circle would be. Well, we could keep doing this with increasingly number of sides to our polygon. And this was finally formalized in the idea called the method of exhaustion. It was really first put forth scientifically by the Greek mathematician Eudoxus in about 370 BC. And he's really the one who kind of verbalized this idea that if we used polygons with increasingly large number of sides, that we could get a better and better estimate for the true area of the circle. It wasn't until Archimedes came along, Archimedes of Syracuse, who really made the most significant contributions to this around 225 BC. Here you see one of his drawings. And he was really the one who eventually came up with pi. He is the one who discovered pi, as really his work was circles, and he kept comparing the ratio obtained by taking the circumference of a circle, because they knew how to measure circumference pretty easily, and dividing that by the diameter of different circles. He always found that you got the same ratio, and that ratio became known as pi. Archimedes has become one of those mathematicians about whom we've wondered what would the world be like, what technological advancements might have been made had he lived, or at least if his writings had survived. Very recently, in years, some writings of his have been discovered and taken a look at. So let's fast forward a little bit from these ancient Greek times to how it relates better to what we're talking about today. So let's fast forward to about the 16th century or so and think about what happened historically between the time that Archimedes was killed and the 16th century. The world went through the Dark Ages in the 5th century after the fall of Rome in 476 AD. And during those Dark Ages, as I'm sure you've learned, pretty much nothing got done intellectually. Any work that was being done intellectually and academically were really being done by monks in monasteries across Europe, but that's about it. They spent a lot of their times transcribing texts since they did not have a printing press, and that's really how they spent their time. We went through the plague in Europe during that time, during the Dark Ages, and really no advancements intellectually or academically were really made. It was right around the start of the Renaissance in the 14th century that people literally started waking up mentally. And that's really where all this now brings us to. Algebra was invented along the way. That came on the scene in the late 1500s, especially put forth by the French mathematician Francois Viet and his writings. Algebra, though, really does trace its roots back to 9th century in Persia. The word algebra is actually derived from an Arabic word, al-jabar, and that's really where it came from. So think about what's going on. We have the discovery of algebra, if you want to put it that way, as a discovery, formalization of algebra, maybe you want to think of it that way, right around the late 1500s, and it's soon after that mathematicians started taking a look at algebra and started thinking about those problems of old. They talked then about finding area of a circle. Well, now we have algebra and curves. That's really what led to the idea of finding area under a curve. So this is really now in the midst of the Renaissance, late 16th century, 17th century. So we're talking like 1600s. Brainstorm a little bit. How could we find the area under a curve? And think about what we talked about with the method of exhaustion. Well, maybe we could use rectangles. We know how to get area of rectangles. So maybe inside that curve, we could put a whole lot of rectangles and find the area of all of them and add them up. That might be a good way to get an estimate for the area under the curve. Would definitely be an underestimation though, and you can see all the empty space, all the negative error that would result. But not having a better way might be a good way to at least get an estimate. You can notice that the rectangular areas wouldn't be that hard to find. Notice they're all the same width, and really all we'd have to determine is the height, and just use the idea of width times height for each of the rectangle areas, and then just add them up. Well, instead of having the rectangles inscribed underneath the curve, as you see here, perhaps we could have them circumscribed and jutting outside the curve a little bit. That, of course, is going to result in an overestimation of the true area, and you end up with positive error. You can see all those little rectangles jutting outside the curve there that are being pointed to. And this is really what mathematicians started playing with, is how could we get area under a curve? And this whole idea of using rectangles was a really good idea, simple to do, and this really led to different types of approximations that we're going to talk about. So as you've just seen from those diagrams, you could use either inscribed or circumscribed rectangles either under or about the curve. And depending upon how you configure those rectangles, you end up with three possible different approximations. You could have a left endpoint approximation in which the top of the rectangles are all hitting the curve on the left side of the top of that rectangle. You could have a right endpoint approximation in which it's the upper right corner of each rectangle that's hitting the curve. Or you could have a midpoint approximation where it's the top middle of each rectangle that is hitting the curve. Now, of course, there's other ways to configure these. If you take a look at these diagrams, you'll notice that this is kind of a mix-mash of a whole lot of different ones. We're going to have a name for that later. where it's not necessarily always the upper left corner touching the curve or the upper right corner or even the midpoint. But these are just three possible ways you could estimate the area under a curve. And we're going to explore these now and talk about how we could actually do some calculations with this. There are two graphing calculator programs that hopefully you have, and we're going to walk through both of them using the two problems that we have as examples. The one is called int_maths. This gives the values of the left, right, midpoint, and then two other types of approximations you're going to be introduced to, the trapezoidal approximation and Simpson's approximation. The area program, though, is the one we're going to use at first because that does a great job. It actually draws it out for you. It actually gives you a visual of what the right, left, and midpoint approximations look like when you draw them out. So let's take a look at a couple examples. So the first one we're going to do is to find an approximation for the area under the curve f of x equals sine of x on the interval from 0 to pi over 2 using 4 subdivisions. So what that means with the 4 subdivisions is that we want to have 4 rectangles to use to find the area under the curve. All right, so let's go over to the calculator, and under y equals, we'll put sine of x. So I have a really good window that we could use to set it up. Let's do 0 to pi over 2 for our x's. And let's do an x scale of pi over 4. For our y's, let's go from a negative 0.25 to a 1.25. And we'll use a scale for the y's of 0.25 as well. So if you go ahead and just hit graph, hopefully everybody's looks like this. So we're going to go ahead and run that area program, and I'll show you how it works and how it gives you the different approximations and what they would look like. You go back to your quit screen and hit your program button. You should notice that all your programs are alphabetized. You might not have all of them that I have here that you see in my list, but go ahead and run that area program. Just hit enter and you'll notice it pops up on your blank screen as program area. Hit enter again. It's going to ask you first for the endpoints of the interval, entered as A and B. So that's going to be 0, and then hit enter and you'll notice it prompts you for B. So that's pi over 2. Number of subintervals, remember we wanted to use 4, and hit enter. And you'll notice it goes back to the graph. It draws the curve, and now it's going to draw your rectangles, and this is what a left endpoint approximation looks like. Notice how it's the upper left corner of each rectangle that's hitting the curve. Now this first one, you'll notice it basically has a height of 0 because the upper left of the rectangle is actually over here at the origin. So this is what visually a left endpoint approximation looks like. And you'll notice in the upper right of your calculator that it's still working. So hit enter and you'll notice you get the decimal value of the left endpoint approximation. Now if you hit enter again, you'll notice in the upper right corner your calculator is still working. Hit enter again. It's going to redraw the curve, and now it's going to draw for you what the right endpoint approximation would look like. And notice now it's the upper right corner of the rectangles that are hitting the curve. So hit enter again, and there's the right endpoint approximation. So in this case, and if you think about what the picture looked like, remember with the right endpoint approximation, the rectangles were kind of jutting outside the curve. So that's going to be an overestimation of the true area under the curve. But you'll notice your calculator's still thinking. So hit enter once more. It draws the curve, and now it's going to give you the midpoint approximation. And if you take a close look at how these rectangles are, you'll notice it's the upper middle of each rectangle that's hitting the curve. And if you hit enter one more time, there's the midpoint approximation. Now a lot of people think that the midpoint approximation is simply the arithmetic average, the mean of the left and the right endpoints. So if you were to take the left and right endpoint approximations, add them together, and divide by 2, a lot of people think that's where the midpoint comes from. It's probably going to be pretty close, but most likely not exactly on. Okay, so that is going to be, you'll notice that the midpoint approximation does always fall in between the left and right endpoint approximations, but it's not necessarily the exact average of the two. Let's run through the next example, and then I'll show you how to break out of the program when you're finished. Now we're going to look at a rational function, 8x over x plus 1, bounded by x equals 0, x equals 4, and y equals 0. You're asked to find the lower sum, upper sum, and midpoint rule. And we're going to use 10 subintervals, so we're going to have 10 rectangles under there. Midpoint rule is the midpoint approximation, but notice how they're referring to the other ones, the lower sum and the upper sum. That's left to you to figure out which of the right endpoint approximation and the left endpoint approximation is going to be either an underestimation, a lower sum, or an overestimation, an upper sum. You might just have to run them both and then figure out which is which. So let's go back to our calculator. Right, go back under y equals, and we'll get rid of that. And the equation was 8x over x plus 1. And you could do zoom 6 to graph it if you want, just to see what it would look like. It's obviously going to be a rational function with a vertical asymptote at -1. And we're trying to find the region bounded by x equals 0, so that's your vertical axis right here. X equals 4, so imagine a line over here at x equals 4 vertically, and then y equals 0. So we're probably talking this little corner here under the curve. All right, but let's set up a nicer window because remember we want to see 10 rectangles under there. So for our x's, let's do -1 to 5, and let's just leave that as an x scale of 1. And for the y's, let's do -2 to 10. So if you go ahead and hit graph, now remember I did go a little bit beyond where we're going to see. We're only going up to an x value of 4 with this, but in between 0 and 4, we're going to have to get 10 rectangles in there. So let's go ahead and run the program. Go back to your quit screen, bring up program again. A in this case would be 0. B is 4. You're always using x values for those, remember. 10 rectangles. So remember it's going to do the left endpoint approximation first. So you should be noticing how it's the upper left corner of those rectangles that are always hitting the curve. So hit enter once more, and there's the value of your left endpoint approximation for the area under the curve. Right, let's run it again, hit enter again. Now it's going to do the right endpoint approximation. So the left one, remember, was an underestimation. Notice how these right rectangles, the ones that are aligned to the upper right of the rectangle, notice how some of these are jutting outside. So it's the right endpoint that's going to be the upper sum, the overestimation. That left endpoint approximation was the underestimation, and therefore the lower sum. So hit enter again. And you'll notice it is definitely bigger than the first approximation you got. We'll go ahead and run the midpoint, and I'm guessing it's going to fall somewhere in between the two of those. And notice how it's the upper middle of the tops of these rectangles that are hitting the curve. Hit enter again, and there's your midpoint approximation. Should you ever need to break out of a program, easy to do, just hit the on button. Pretend you were in the middle of running it and you decided you wanted to back out of it. Just hit your on button in the lower left, and it's going to, give you the option either of quitting the program or if you want to continue. So I want to quit out of the program. Just hit enter, and you'll notice then you can just hit clear and get your blank screen back again. So where we're going to go from here, now that you've been introduced to left, right, and midpoint approximations, is we're going to talk next about what would happen if we wanted to vary the widths of those rectangles. Remember, all these rectangles were the same width. All right, but maybe if we were to vary the widths, we could fit more rectangles under the curve better and maybe get a better approximation for the area under a curve. So stay tuned.